Afternoon, everyone. My name is Norbert Barszczewski, and I'll have a pleasure of moderating the session today. Our last session for today. So we have four nice speakers. One looks like on the way. Hopefully, Julie will be here also here today. The first presentation comes from company Jenike and Johanson, who is a world's leading company in powder and bulk solids handling, processing, and storage technology. Most of us know the company. It's one of the giants in the industry, so it doesn't require a lot of introduction. And we have here with us today Dr. Jayant Khambekar, and he will talk to us about addressing feedstock handling challenges with municipal solid waste and biomass.
Thank you. Good afternoon, everyone. So far, most of the presentations that we have seen, in my view of the world, they were more focused on, what's the technology or what's the end product that we are using waste to convert to. But as far as my presentation is concerned, it is more about how do you get your waste to that reactor point or reaction point, whether it's incinerator, whether it's pyrolysis reactor, whether it's some other process. How do you get your waste material, your waste feedstock reliably up to that reactor so you can produce a good and quality product and the process is reliable? So about Jenike and Johanson, really quickly, we are a technology provider company and consulting company. We work primarily in the area of achieving reliable flow. How do you achieve reliable flow of bulk materials? And we provide customized design solutions for various storage and feeding applications. And this applies to new installations as well as retrofit projects. The technology of solids handling, and when I say solids handling, some people call it solids, some people call it bulk solids, some people call it bulk material. They are essentially the same things from our perspective. So this technology that we use is based on the work done by Dr. Jenike in 1950s and 60s. He founded our company based on that theoretical development. And here we are 55 years down the road, and we have been using this bulk material handling technology really for all kinds of industries, wherever there is bulk solids handling application. So whether it's mining, whether it's plastics, whether it's biomass, or whether it's waste materials. And sorry for I think we did some last minute conversions from PDF to PowerPoint. So you may see some text realignment. I apologize for that. But typically in any project that we do, to get to that customized design solution, the steps involved are testing of your feedstock, then analysis of its flow behavior, and then coming to that reliable design recommendation. For this presentation, my focus really is on these feedstocks: municipal solids waste, RDF, biomass waste, and plastic waste or recycled plastics. And I guess based on the earlier presentations, we should also add probably SRF here. Or any kind of bulk material that's used. And when you are working with bulk materials, you will see them used in various different locations from operations or process perspective. So you may be handling them in the receiving yard, you may be handling them for your size reduction process, you may be handling them for your drying process, or you may be just storing them in bins, silos, or hoppers, or you may be feeding to a reactor going to a high pressure, high temperature environment. And as far as this presentation is considered, the focus is how do you get to each of these unit operations reliably without experiencing stoppages in flow behavior, without experiencing plugging issues or bridging issues. And as I said, this presentation really applies to any kind of bulk material feedstock. So whether it's municipal solids waste, whether it's biomass, crop waste, or plastic waste, or recycled plastic. And just to kind of orient ourselves, in case you're not attuned with the day-to-day operations of bulk solids handling. So for typical, if you look at any kind of waste conversion process, whether it's plastics waste, whether it's biomass waste or any other kind of waste, you may have, when you're looking at handling in the yard, primarily there is a storage facility. It can be an open storage, like a stockpile or pile in the yard, or it can be a covered storage, for example, a covered warehouse, for example, where bales can be kept. And you will need to reclaim reliably from these kind of storage situations. Then there can be storages such as silos, large silo storage, or there can be small hoppers which you will be feeding out from. And this discussion applies to all those equipment. So first, let me introduce you, or many of you may already be familiar with the various flow issues that can occur when you are handling your feedstock. So one of the biggest problems that you will see, especially when you are handling these feedstocks through bins or hoppers or silos, is arching or bridging problem. So here, for example, you are looking at your silo or bin, and you are looking at the feedstock stored in there. Now that can be, for example, again, your municipal solids waste, or it can be biomass or some other raw material. And based on the characteristics of that feedstock and based on the design features of that silo, and by design features, we are talking about the diameter, the height, the hopper angles, the outlet size, the internal surface and smoothness of it. All those play a role in determining the net flow behavior. How does it perform? How does it operate? Does it give you reliably the discharge rate that you are looking for? So all those factors together determine that. And if the design is not adequate for the material to be handled, then you may experience problems such as bridging or arching. So here is a schematic again that shows what that problem looks like. So when you have material in the silo or in the bin, and you are trying to discharge from the outlet, when this problem occurs, you will have an arch-shaped obstruction over the outlet. And when this happens, the discharge stops. You are not getting any material out from that bin or hopper or silo. And what that will result in is you will essentially starve your downstream process. So it has significant implications as far as why we have to get this right. For materials like wood chips, for example, you can see those materials forming arches because of interlocking. Whereas for some other fine feedstock, having a lot of fines in it, you can see what we typically call as cohesive arching. So both of those can occur depending on properties of the material. Another important problem to be aware of is rat holing or channeling. When this type of problem occurs, again, we are looking at a silo or bin, and the materials inside But when this problem occurs, a channel forms directly above the outlet of that silo. And material flows primarily through that channel. And once the channel empties, then no material is coming out. All of this materials here is just sitting stagnant. It's not moving. It's almost like a dead capacity or dead material. So unless something happens, either you use a lot of vibrators, you use air cannons, air blasters, some kind of aids to get that material moving. Unless you do that, it's not coming out. And it's occupying all of your precious storage capacity. So again, same kind of implication as bridging problem, that when this problem occurs, you are not getting material out of the silo and you are starving the downstream process. Here is an example. We are looking inside a silo and we are looking at this flow channel here and all the dead capacity that's not discharging. So we talked a little bit about designs of silos and hoppers. And again, this, when I use the term silo, it really applies to any kind of storage equipment that is based on gravity flow. So applies to hoppers, bins. But the other important piece is the feeder beneath the silo, whether it's a belt feeder, whether it's a screw feeder. The purpose of the feeder is to withdraw material from the entire outlet of the silo or bin. When the feeder is not designed properly, what it does is it often pulls a channel in the hopper section directly above it. So even if you do a good job with getting the silo designed correctly, if the feeder design is not correct, then you're still going to have problems in your hopper or silo. And that's still going to starve the process. That's going to result in erratic flow, unreliable feed to your reactor, incinerator, furnace, boiler, as the case may be. Here is an example of a rat hole, a channel that has formed inside a hopper. So you see the problem here was the feeder design, where the screw feeder had constant pitch section. So the distance between the two flights did not increase, which meant that you had the same capacity. Once the first pitch was filled, all of that material, as the screw turns, will go here, and all of that material will go here. So there is no additional capacity increase to pull in rest of the material. And that's why all of this material remains stagnant. So these kind of design features can really play a substantial or critical role in the success of your reactor or whatever is the end process unit. So again, really important to get the design of the feeding system, the storage system correct. Another thing to keep in mind is these materials, oftentimes when we're talking about MSW, biomass, they tend to be very compressible, and under certain conditions, they can exert significant amount of pressure because of packing. And oftentimes, it will result in issues such as failing of flights, so flights breaking off or welds coming off. So those kind of issues can also occur when you are handling these materials, especially if the design is not correct. Drag chains are commonly used as conveyors, but if in case when they are used as feeders directly underneath a silo or a hopper, then they experience significantly higher pressures. And in those cases, you can also see the flights breaking off because of the pressures and compactions. So when you look at these problems, ultimately, what are these problems costing? They're costing downtime. They're requiring manual intervention. they're causing lost production. And often cases, whenever these problems occur, you're not able to either supply to your reactor or downstream unit at all, or maybe you are able to supply, but it's not at a consistent rate. There is no steady inlet or input stream to your reactor, and then that messes up the operation of the reactor. So all these issues can occur, and they can take away the reliability of the process. So sometimes, people look at material handling and say, okay, we figured out the chemistry, we know how to do this, we are all good. But if you can't get your feedstock reliably to the reactor, then problems can still occur. So why do these problems occur? They can occur, one, because of the nature of material or feedstock that you are handling. Typically, whenever we are looking at waste conversion technologies, most of the feedstocks, whether you are talking about MSW, whether you are talking about biomass or crop waste, these tend to be lightweight, having particles that are very asymmetric, slender, having nesting tendencies, interlocking tendencies, and oftentimes with significant moisture content. And it's the combination of these things that really makes that feedstock challenging to handle. Secondly, feedstock is only one side of the coin. You also have to look at your bin or silo or hopper and feeder design. Even if you have challenging feedstock, if you design the handling system correctly, then you can still get reliable flow. But if the features of the handling system, such as hopper angles, outlet sizes, the surface finish, if those are not properly done, then you can have flow issues. And sometimes you will see that, we all understand that cost is very important and critical in helping any project go to completion. But due diligence should be exercised when you are selecting cost over reliable flow. You need to consider all the possibilities. You need to make sure that you are able to get the feedstock reliably to your process before you make or you put too much emphasis on the cost. And again, I apologize for the last-minute conversion, so which has moved things, which has moved text around a little bit. But as far as solids flow is considered, as I said, it's a function of material flow properties as well as design features. And the material properties that are particularly of interest are cohesiveness or stickiness of the material, its interlocking tendencies, the friction between your material and the internal surface of the hopper, compressibility of the material. And those characteristics need to be understood. In the projects that we do, we conduct testing of representative samples in our lab, and we obtain data on these properties as a function of particle size distribution, as a function of moisture content. And using that information, then we conduct design activities to select proper hopper angles or outlet sizes or surface finish. And when you combine these two, characterization of the properties of your material and appropriate design for the handling equipment, then you get reliable flow. So ultimately, the flow pattern, as it's called, that occurs inside a bin or silo is dependent on these things. And there are two main flow patterns. There is funnel flow, where, in some of the earlier slides that we saw, you have a channel that forms directly above the outlet, and a rat hole may form if material has sufficient stickiness. with stagnant material around it. So this problem occurs when the friction at the hopper walls is so high that it causes this material to remain stagnant. And what goes wrong when you have a problem like this? Obviously, there is channeling that occurs. You get a first in, last out flow sequence, because whatever comes in first in this silo, it goes here and stays there until all of this empties out. Rat holes can form, and then you have limited storage capacity, again, because of this dead material just sitting here. Erratic discharge occurs, and particle size segregation issue gets worse. So whenever you are handling a feedstock with fines as well as larger coarse particles, usually when you fill a silo or bin, what you will see is that the bigger particles, they concentrate towards the walls. And the fines, they concentrate in the center. I mean, think about large stockpile. And if you have rocks and fines all going to the stockpile, you will see a lot of times the large pieces of rock concentrated towards the periphery of the pile. Same thing happens in your silo. And when you have funnel flow, because you are having channeling, flow is occurring through that central channel, you are primarily withdrawing fines first. And then later you are pulling all those coarse particles. So again, this can have significant implications on your downstream process. If you are sending it to a reactor that is very sensitive of the particle size distribution, then it can upset the operation of the reactor. So funnel flow has a lot of issues, and a good design should try to achieve what is known as mass flow. So mass flow is defined as a flow pattern where all of the material is in motion when you are discharging. There is no stagnant material. And this doesn't happen on its own. You have to design the hopper or silo features, the hopper angles, outlet sizes, surface finish, all of that appropriately so that everything is moving when you are discharging. But the benefits you get out of it are first in, first out, because again, there is no stagnant material. Rat holes cannot develop here. There is no channeling. And you get full storage capacity. All of the capacity is live. There is no dead region. You get uniform discharge, and segregation is minimized because in mass flow, everything is in motion. So as you are discharging, material in the center mixes with material at the hopper walls at the point of discharge. And because of that, even if your material separated or segregated in the silo, at discharge, there is some remixing that goes on. So it reduces the amount of segregation that you see. So a lot of benefits to achieving mass flow. But again, it just doesn't happen on its own. You have to characterize the material. You have to design appropriately to achieve that. Okay. So for how do you conduct proper design? Well, you conduct the characterization, get the properties of your material, and accordingly, you design your silo or feeders or other storage equipments, and keeping in mind that these properties depend on particle size distribution, moisture content, among other things. And when you do that, you can design your storage equipment to achieve reliable flow. Here are just a couple examples showing how reliable designs look like for typical biomass materials. Here is just a design. Here is a separate one, not this kind, but separate one. That's our patented converging, diverging silo design. And with that, I would like to conclude that technology is available to characterize feedstock and obtain that information to design material handling equipment. And the design activities should be done especially considering type and nature of feedstock, particle size distribution, as well as moisture content. And doing so can save a lot of headaches with unreliable material flow. So with that, I would like to thank you, and I don't know if we have time for
Yes,
questions.
we have time for a few questions.
Okay.
Thank you, Dr. Khambekar. Do we have any questions? Yes, we have a question in the back. Thank you. It's okay.
Those airlocks complicate the situation, and how you deal with them when you have a system that you have to have an airlock like a rotary airlock or knife gates and all of these kind of different.
Right. So I guess one way I can answer that question is rotary. So we kind of talked a little bit about belt feeders, and we talked about screw feeders, but rotary airlock is another type of feeder, or it can be used as a feeder, and it has its own considerations which are separate or different from what you would have for a screw feeder or what you would have for a belt feeder. But it is also important for a rotary airlock to make sure that when you use that as a feeder directly beneath a hopper or silo or bin, to activate the entire outlet area. So oftentimes, if it's not done properly, what happens is you have a hopper section or a bin, with convergence, and you put rotary airlock directly underneath it. Because the way rotary airlock works, there are pockets that move, and as a pocket comes up, it's empty. It pulls material from that one part of the outlet, and as it moves further, now that pocket is full and it cannot pull in any additional material. So it basically forms channel if it is used in that manner. So oftentimes what is a good thing to do is put a straight section right above that rotary airlock so that any channel that occurs there can expand to the full outlet size. So yes, short answer is even rotary airlocks, when you're using them as feeders, you have to use appropriate considerations from a flow perspective.
How reliable do you think are similarities to test smaller prototypes for scaling?
That's a good question. So the tests that we do, are bench scale tests, and based on 55 plus years of experience, for many of the aspects, not all, but for many of the aspects, we see that the results that are predicted from our bench scale tests, they apply to large scale installations as well. But in some cases, especially when you are working with very compressible materials, and you want to store very large amounts inside a silo, for example, then you really need to be careful. You have to add some factor of safety on top.
Thank you very much, Dr. Khambekar. Very good presentation. Very little technical, but very informative. So thank you. We'll try to have some time at the end for more questions, and definitely during the reception. Thank you.
Thank you.
Our next speaker is Tony Lubiani, General Manager of BlackRock Material Handling, BMH Technology. And Tony will talk to us today about large-scale waste-to-fuel feedstock preparation. I can tell you this, any company that calls its main product Tyrannosaurus, I want to sit on that session and learn what it's all about. Thank you.
Good. Thank you. Appreciate you being here today and for our presentation. I'm Tony Lubiani, General Manager for BlackRock Material Handling. The presentation is for our European partner company, BMH Technology out of Rama, Finland. Peter Willenius prepared this presentation. He's the Senior VP of Sales for BMH, and obviously was unable to be here to get into the country. We did offer him a Mexican travel agent to help his travels, and he said no. So BlackRock Material Handling, we're an engineering company out of Greenville, South Carolina. And I mentioned BMH is our European partner out of Rama, Finland. They've been in business since 1929. And in Finland, obviously, they started out in biomass, in the pulp and paper business, and in energy. In the 1990s, I started working with them in pulp and paper plants, energy plants, biomass plants, providing their equipment, service, and sales to the North American market, US and Canada. In 2000, they refocused, because of the drop in pulp and paper opportunities around the world, they refocused their designs on in waste to energy type equipment. So they redesigned their product line, designed a shredder to be the heart of their system. And so their focus now is in waste refining solutions, solid biofuel, and then their services department. They're focused, and their customers include power plants, chemical recycling. They still do some pulp and paper, a lot of cement kiln feeds, because we're preparing SRF, RDF from MSW, and biomass. They've delivered, since 2002, they've delivered over 65 large waste handling projects, and the wood bio-based handling projects are in the hundreds. And their installations are global, obviously in Europe, where waste to energy is an accepted technology. North America, less so. So their installations are everywhere but here. And we're looking to help change that for them. So they've, you mentioned the trademark is the Tyrannosaurus. They latched onto that. They were looking for something that would help show what they were targeting their equipment to be, the biggest and baddest shredder handling equipment on the market. So the other focus they did is they looked at modular design and a compact design. Real estate's always at a premium, and with a minimum footprint. So depending on the feed material and the fuel specs that you require for your processes, these large capacity facilities will typically require multiple lines of equipment processing between 30 and 50 metric tons an hour. So anytime I say tons today, I'm going to be talking metric tons. We mentioned the modular approach, and it's typically the scope of work is broken into 3 modules: the receiving and crushing, a separation island, and the storage reclaim metering island. All of the components in these were designed specific by BMH for waste handling and or biomass, except for magnets and eddy currents, which is the way they buy out. For the waste processing, waste to fuel and feedstock preparation, in the components in each of the modules, such as receiving and crushing, you have the step feeder, which is your large live buffer before the shredder, and it's got an automatic feed control to continually feed the shredder as it needs more fuel or needs more material. The shredder, this particular model is the T9905, which is the largest unit they provide. Capacity of 30 to 50 tons an hour, and that can make a product size less than 50 millimeters. Typically, a lot of their facilities, they're feeding circular or CFB type boilers for energy in other in other areas of the world, which will take up larger products up to the 100 millimeter. But we're seeing for gasification projects where targets a lot smaller, around the 50 millimeter target. In the separation section, you've got the what they call is the MIPS design that they provide. It's really it's integrated into the shredder. It's a massive impact protection device to take out unshreddable contaminants from the feed. Of course, you've got the magnet, fine screen if required, eddy current and an air classifier to take out the heavy fractions. And in the storage, as the good doctor said, you're looking, you're looking to make sure that your silo is properly designed. This is a full live bottom circular screw reclaimer for the silo. The feed is a distributing feeder. It gives you good distribution of the material to give you more of a blended feedstock. And then the metering screw afterwards will reclaim at the rate that your process is looking for. And what is the Tyrannosaurus process, the benefits? So one, it'll handle a wide range of residential and industrial waste. It's also, they're very familiar with geographical differences in the waste supply. Obviously, North American waste, European waste, and Asian waste are all different commodities in that product, and they certainly understand all of those waste streams. High capacities is one of the things they targeted in designing the system. They wanted to make it compact but easily scalable by adding additional lines as your capacities increase. It's fully automated, so your manpower to run this facility, you have an operator, and then if you have a tipping floor, if you're manually feeding the feeders, you may have 4 or 5 guys on the feeding the step feeders, or if you have a crane operator from above. It's a closed system. All the equipment is enclosed. All of the drag chain conveyors feeding from island to island are enclosed. And that gives you the dust and odor control you're looking for in your system, and also eliminates spillage issues. The system has a negative air pressure and filtration system through all the conveyors and equipment, again, to help support your odor control, and dust explosion designs as required. And BMH is a complete solution provider, so instead of you having to go to multiple vendors to cobble together your screening system or your shredder system or your storage reclaimer system, BMH provides a one-stop solution. Slightly different approach on the biomass, if you're taking a biomass to a fuel feedstock process. So still the modular approach, but your in-feed, you can receive material that's already been sized, so there's no reason to take it through a shredding process or a crushing process. The screening system typically is a little more simplified. You're typically going to take maybe fines out if you want to, or to be a screen to take out the overs, and then a secondary small crusher to make sure that fraction is sized proper for your process. Storage reclaim, again, is very similar to the waste process with circular silos or large A-frames with underpile reclaimers to give you first in, first out opportunities. And again, the components in the biomass system, the shredder's a little different. The T9905 on waste is specific for waste. Let me back up one. I'm sorry. I should have told you a little more about the shredder, the Tyrannosaurus shredder. So again, that shredder is the heart of their system. It's a ram-fed monoshear shredder, slow speed, 50 to 100 RPM. It's a large diameter, 1 meter diameter rotor, and the width of it's 4 meters. So you've got a very wide feed opportunity, crushing opportunity. But it's broken into 5 sections. Each section's 800 millimeters wide, and that's part of the MIP system. If you get a non-compressible in there, the machine will stop, open up that section, drop out that contaminant. Instead of unloading your entire shredder, it'll only unload the section, get rid of that contaminant, close back up automatically, and go back into operation again. So what that does, again, it helps your uptime in eliminating the stoppage and going back to work again. Zero gap cutting technology on this shredder. It's a very, very tight cutting tolerance between the cutting knives and the anvils, and it's hydraulically adjustable. So at the end of each shift, you can adjust your gap on your knife cutting quickly. And each knife rotates 4 times before you have to change knives again. All right. We talked about we jumped ahead to the biomass. So the shredder for the biomass is a twin rotor gravity-fed shredder. Its largest unit they've got is a 6-meter-long in-feed, 6-meter-long rotors for a very large capacity. It's a slow-speed shear shredder, or twin shredder to minimize dust generation. In the screening, again, the quality preparation, you can have your ferrous removal, oversized separation, and additional crushing. And we'll go over some specific installations that they've installed. The first one is for Maller Energy in Sweden, in the town of Västerås. This is a 3-line system, and their input into the plant is industrial, commercial, and MSW. This particular plant handles 480,000 tons annually. At the time, is the world's largest integrated waste processing, along with the power boiler, CFP boiler. The plant is, I mean, even though you see the field behind it, on this side of it is right up against the town. So they're very proud of the facility, and they love to give tours. So when the world opens back up again, we'll be more than glad to help you arrange to see a tour of this facility. It's quite beautiful. Nice grass roof. Another facility in South Korea was installed and started up in 2016. It's a 2-line system. It's 300, everybody's heard that magical number today, 300,000 tons a year for the feedstock. And this is just an SRF fuel preparation. So they take the material and then they sell it to the market, either as for cement or energy production. And last year, they shipped in and started up a plant in the Middle East, out in the middle of the desert. They don't require enclosed buildings. You've got a lot of dry heat. This was a 2-line system for industrial, commercial, municipal solid waste, and at 320 tons a year. And for biomass example, in Spain in 2020, they started up a very large facility, 550,000 tons a year, processing biomass, forest residues, eucalyptus, whole wood, branches, tops, and trees. And and that's feeding a 130 megawatt bubbling bed boiler. And again, these have those 4 of those very large, this is a 4-line system. Very large shredders are in these. And then the current system under construction is Interchem up in outside of Montreal in Varennes, Canada. This system is integrated both, one line is for waste line shredding. The other line is for biomass. Both those lines will be fed separately, screening separately, and then that material will be mixed into a buffer silo before the dryer. And then after the dryer, it goes to another storage area before they feed the gasifier. Our feedstock capacity on this particular plant is 300,000 tons a year. And we're looking for a startup in 2023 for this unit, for this facility. And hopefully we've got a video queued up. Ted, partnered today with me is Ted Gentile, is our Vice President of Sales. Is this the Västerås video you sent? Which one? The waste processing video. Okay. or not. It was very nice. Sorry I missed that. All right. So in lieu of the video, unless maybe for dessert, Ted will give you the thumb drive and you can run it later. All right. Well, I appreciate your attention today, and if you have any questions. All right. Thank you very much.
Do we have any questions for Tony? Okay. Thank you very much. A truly impressive piece of equipment with a catchy name. And by the way, BMH Technology is one of our sponsors and exhibitors, so they have a booth in the exhibit hall. Please stop by. Do you have a screen you can play the video over there? Oh yeah, that's a perfect stop for the reception. Our next speaker is Brian Schellati, Director of Business Development from Dyke Recycling Solutions, another one of our sponsors and exhibitors. Brian, take it away.
Good afternoon, everyone. I have a couple videos in my presentation also, so I hope I have better luck. But I want to first thank Gene and the Waste Conversion Conference team for having me here today to present on two unique and fairly new pieces of equipment from Dyke Recycling Solutions to not only maximize the diversion of organics, to meet regulations like California's SB 1383, but to also maximize the value from those organics. I'm going to first give a brief company overview, then talk about each piece of equipment, explain how it works, and then show a video of each of them from some of our recent installations here in California. So first, Dyke Recycling Solutions is a turnkey sorting system supplier. We design, engineer, supply, install, do startup, commissioning, training, and after-sales service of all of our equipment in many mixed material applications, such as single-stream recycling MRFs, construction and demolition debris processing, obviously MSW and mixed waste processing, compost processing, e-scrap, and many more. We just moved our headquarters to Norwalk, Connecticut, where we actually have the world's largest MRF education, testing, and training facility on site. We have 10 regional sales offices spread around North America, including 35 factory-trained service technicians throughout North America, including Canada and Mexico. We put a real strong focus on service and making sure that all of our plants in operation experience minimal downtime. And one of the many ways we do that is we keep over $19 million worth of spare parts in our Connecticut warehouse, which has at least 2 of every spare part required from any of our pieces of equipment all over North America. We were founded in 1984. Since then, we've completed over 1,800 recycling projects. We've delivered over 450 full turnkey MRFs or plants. That includes over 550 sensor-based sorters or optical sorters and over 400 bolograph balers. This is what our new test facility in Norwalk, Connecticut looks like. Basically, we could take samples of mixed materials from our customers or from companies, and we can run it through our test facility, run the test, create a test report, be able to give real estimates on equipment capacities. We are able to give real estimates on what is in the material that's being processed or what's in the sample, what of those materials can be recovered, and to what level or purity that material can be recovered. It's already been extremely valuable for several project developers, MRF operators, and also packaging companies. So the first piece of equipment I want to speak about is called a Smecon Organics or food depackager. There are several other types of depackagers that specifically California, some California waste haulers are already starting to use. This one is a European model. It was developed and really field proven over in Europe for over 20 years now. There's many of them in operation in Europe. We've actually just had our first one installed right here in San Diego that is now operational. Really, the main function of this food or organics depackager is to process expired, packaged grocery store waste. It can also process any contaminated restaurant waste or contaminated food industry surplus. Really, the function is pretty simple. The contaminated organics goes into the piece of equipment, and really the outputs are a clean, wet organic fraction and then a clean, dry packaging fraction. The wet organic fraction can be used for animal feed, it could be used in composting, it could be used in anaerobic digestion for reusable energy. And the dry packaging fraction, depending on the type of packaging, can obviously be recovered for recycling, or it can be made into an alternative fuel. The function, as I said, is pretty simple of this piece of equipment, but the engineering and the mechanical details that go into it, at least go into it to make it operate well, are actually pretty complex. So this slide goes over a few of the major advantages of this specific depackager. First thing to point out, one of the main advantages is actually that this one operates at an extremely high throughput at roughly around, really over about 30 tons per hour, and with minimal downtime, really regardless of any type of input contamination. So how does it do that? A couple key features. First, it has the original swing hammer design, so the paddles inside the unit, which actually you could see here, they're flexible. So if a heavy piece of contamination, like a big piece of steel, goes into the piece of equipment, it's flexible enough not to have that piece of contamination damage the screen inside or just cause any unexpected downtime. Also, there's an extremely large inlet, and then below that inlet is where we have the smallest holes in our screen, and that's really to maximize the organics, maximize or keep the organics as clean as possible, really, in that impact area at the beginning. After the input area at the beginning, the additional screen sections are extremely customizable. So meaning, we can vary the size of the screening holes depending on the objective of the depackager. Is it, is the objective to maximize diversion of organics, or is it the objective to maximize the purity of the organics? So that's something we can play with in this depackager. Also, the screening sections are on a rotating drum. And that is very unique, and it allows the operator to easily rotate the drum when it needs to be cleaned or to perform maintenance on the depackager. Let's see if the video works. There we go. So this is actually a video of one of our mobile demo units. It's a full-scale unit that we can send to a customer's site to do a demonstration and to process some of his actual material. You could turn the sound off. So you can see they're just setting it up on site. So this is, contaminated, basically source-separated organics, but it has some, obviously, packaging mixed in it with it. So we're separating the organics from that packaging, mostly that cardboard. And this is an example of it running, more traditional grocery store waste, packaged food, food goods. Okay, now so we basically talked about, one way to process wet organics and remove contamination. Now this is this is the next piece of equipment I want to talk about, and it's to remove contamination from drier organics, specifically from compost. So, a lot of wet organics from especially MSW processing usually goes to anaerobic digestion, then composting, or sometimes just directly to composting. And the result is that compost is highly contaminated, and because of that, it has limited or no value. So this is a densimetric table, or we call it D-table for short. It is specifically designed, or ideally designed to be a final composting step or a finishing step for compost. So each unit can run up to about 20 tons per hour, and it will remove up to 99.5% of all heavy contamination, such as glass, stone, and metal. I mean, typically compost from MSW will have upwards of 10% glass by weight in it. So this would remove over 99.5% of that type of contamination. So how does it work? This is a schematic showing the operating principle of the densimetric table. The basically finished compost before this piece of equipment would come through this in-feed section right here. It falls on an angled vibrating plate. There's air from a fluidizing fan that blows up through small holes in the vibrating angled plate. The light fraction, or the compost in this example, would get lifted up by the air, and then with gravity would fall out the bottom side outlet. And then any of the heavy contamination, like the glass and the stone, would sit on the vibrating plate and gets transferred up the plate via friction and falls out the top side outlet. Any very light compost or dust would get pulled out of the exhaust ductwork and goes to the dedusting system. That once that is cleaned up after a cyclone, it can actually be combined back with the finished compost if desired. There's also a sensor inside the exhaust system that simply regulates the exhaust fan. So it's a very simple piece of equipment to operate, literally just an up and down fan control, depending on the moisture of the compost. So another video. So this is an installation at a composting operation in Northern California that is composting very contaminated organics from MSW. We've actually just had a more recent one installed in our new MSW MRF in Santa Barbara, which also has an anaerobic digestion plant in it and composting. So this is the dirty compost before any type of screening. Then you see, this is not a piece of equipment that we supplied. This is just a normal compost trommel where they're doing screening of a 1/4 inch minus. And that 1/4 inch minus is their finished compost that goes to the densimetric table. You see here, this is the overs of that trommel coming out there. That's just a large contamination. All of this separation pretty much happens right here on that angled vibrating plate that I described. So you'll see the heavies come out to the left, the lights or the compost comes out to the right. This is basically the simple control panel. Like I said, it's literally just an up and down control for the fluidizing fan. Basically, the higher the moisture, the higher the fan speed, the lower the moisture, lower the fan speed. So this is showing the heavy contamination, the glass and the stone and the metal and the heavier plastics coming out. And this is the clean compost fraction. Also, you see here the cyclone that would take the, after the dedusting system and the exhaust, very fine compost gets blended back in. And this is pretty much, 99.5% or greater, contamination-free compost, which it now actually has, quite a bit more value than before this finishing step. Without this finishing step, when you see a finished compost pile from MSW, whether there's 2% glass in it or 3% glass or 10% glass, as soon as the sun hits it, it's like a shimmering mountain of dirt. So right away, compost like that gets rejected. That's really it. Thank you for paying attention, and I look forward to any questions. My contact information is here if you have any further questions after the conference.
Thank you very much, Brian. Do we have any questions? Yes.
So real quickly, where would the plastic fraction of that go through the separation process there?
For the densimetric table, the
Yeah.
compost? So it depends on what type of plastic you're talking about. If it's a small piece of rigid plastic from like a container,
Right.
then that would go with the heavy contamination. A piece of film plastic, like a sticker that's on produce, would typically go out in the exhaust system. And if there was a lot of that type of contamination in the exhaust fraction, then we would keep that separate. We wouldn't blend that back in.
Okay. Yeah. Gotcha. Thank you.
Any more questions? Okay, thank you very much, Brian. Thank you. So we always try to save the most entertaining speaker as the last speaker of the day. So here with us is today Julie, who's the Senior Air Quality Scientist from Yorke Engineering. Mic is yours.
Great, thank you. Now we'll kind of change topics a little bit. We'll go into discussing, now that you've got the technologies from these gentlemen, how you can actually permit it here in California. So air permitting, CEQA, and odor issues for organic waste diversion projects in California. As many of you are well aware, there's a lot of key regulations in California. These are the key organic waste diversion regulations that are in the state right now, and they are driving a lot of these organic projects, whether it be waste to energy or composting, et cetera. Yorke Engineering, who I work with, we've permitted a whole bunch of different types of organic waste diversion projects. This whole talk will focus on these different technologies. There's a wide variety that I think most of you are all well aware of. So permitting and CEQA. In California, there are 35 different air districts, and each one permits differently. So that's a real challenge right there in the state. What do the air districts need to look at? Their objectives are to regulate the emission sources, meet new source review, protect public health and welfare, and facilitate state goals like AB 32, which is greenhouse gas regulations and landfill diversion. CEQA, which is the California Environmental Quality Act, has different focus. It identifies on identifying significant environmental impacts and encourages quite a bit of public participation. CEQA is overseen by a CEQA lead agency, which may be the county, the city, it could even be the air district, it could be another agency. There are unknown numbers of CEQA lead agencies. So every time you get a new project, you almost are guaranteed to get a new CEQA lead agency. So you've got another agency to try to figure out and deal with. CEQA is triggered when a project must get a discretionary governmental approval, such as a conditional land use or zoning change, or even some air permits will trigger the need for CEQA. CEQA is analysis of 18 different technical areas, environmental areas, and we'll focus today just on air quality and greenhouse gases. So CEQA and air permitting. Key for before you start your air permitting and CEQA projects is getting your project scope and your emission inventory. Those go into an air analysis, which then will go into your CEQA documentation and your air permitting. It is best if you get your project design well defined without any changes going on or design modifications as you start into the process. Because both CEQA and air permitting need a certain number of analyses, and they're quite dependent on all the different aspects of the design features. It can take longer to conduct the CEQA review than the air permitting, so you would probably want to consider your CEQA review before your air permitting. In CEQA, when you look at CEQA, you need to look at, air permitting actually looks at all just the stationary sources, so pretty much anything with a stack primarily, or anything that's not moving on your site. CEQA also examines your mobile sources, and it examines your non-permitted sources, so small engines, and it also examines your construction of your facility. So for CEQA, CEQA analyses can be a little not as in-depth for a mitigated negative declaration, which is a document that looks at a project that is expected not to have any significant impacts. And that usually can take somewhere in the order of 3 to 6 months to get through that CEQA process. But if you have a more complicated project, you expect to have public opposition or anything a bit controversial, or there may be potential for significant impacts, which could be mitigated, then you'd need to go through an environmental impact report, and those are much more extensive, can take usually on the order of 6 to 24 months. So if you're going to be permitting in California, that's the long lead item, is if you have to deal with an EIR. Air permitting is generally on the order of 4 to 12 months. The other key topic item is that you can't get your air permit until your CEQA analysis is complete and approved. So you need to get through that whole process. So starting early on your CEQA is a good idea, but make sure you've got your design complete before you're starting the process. So that would be defining the project. So make sure you've defined your project well. What your feedstock is, even if it's multiple different feedstocks, what's the maximum throughput of each feedstock? Are you gonna have on-site storage? Process description, what kind of equipment will you have? Will you have engines, turbines, flares, thermal oxidizers, et cetera? What kind of control devices? Are you looking at odor scrubbers, biofilters, et cetera? And will you have any abatement? If you're bringing the organics in, will it be put into a containment, into a building before you do your processing? Air pollutants. So due to the fact that a lot of organic projects have as sort of a newer technology for some of the air districts, making sure that you define what your emissions are prior to starting has a fairly major trickle effect throughout the whole thing, whole permitting process. So you'll need to define what your criteria pollutants are. What are your VOCs from the organics? What's your particulate matter from your material handling and your on-site truck travel? What's your nitrogen oxides and carbon monoxide from your combustion, your greenhouse gases? Even if they are considered biogenic, they need to be well defined. Air toxics, there's quite a few that need to be looked at, and ammonia and diesel particulate matter can be pretty big drivers in your from an air toxic standpoint, and they come from all different sources, like your biogas combustion, composting, stockpiles, pretty much everything. And then odors are, odors in a permitting standpoint are regulated as a nuisance, and in CEQA need to usually have a little more in-depth analysis to make sure that you're not going to be impacting the neighbors. Emission quantifications. So emission calculations are all based on the emission factors, and emission factors that are default are generally tend to overestimate the emissions from facilities like this. Very conservative analyses have been done to develop what some districts may call default emission factors. So you can do one thing that may be of value when you're in your permitting, in your initial part of permitting processing, is to think about doing some source testing to develop better emission factors. And so that it may be, you want to look at source testing from stacks, buildings, combustion sources, or emission monitoring, such as for non-point sources, such as compost piles. So what are the emissions used for? So you'll be using them in the air permitting for new source review. With our 35 different air districts, they all have different thresholds of where you need to meet these different requirements and which one when it gets triggered. So best available control technology will be the controls that you need to put onto your units. In some districts, the threshold for that is it's a per permit unit. So if you have two engines using your biogas, for example, each engine would be examined for BACT, and they need to meet certain permit levels. The trigger can be as low as 1 pound per day for criteria pollutants for BACT in South Coast Air Quality Management District. If you're here in San Diego, our criteria is 10 pounds per day, so it really varies between your districts. BACT, it may be a emission limit or it may be an abatement technology. And don't just think it's just the stacks that need BACT. There's the compost piles need BACT, even your odor control systems need to meet BACT. Then the next one would be offsets or emission reduction credits. Emission reduction credits are for the entire facility, both the existing and new portion, if it's an existing facility. ERCs are triggered as low as 4 tons a year for criteria pollutants in South Coast. In San Diego, in each district, it's based on your attainment status of the different criteria pollutants, and in San Diego, it's 50 tons, so it's a lot different than 4 tons. So each different district has a significantly different thresholds. Health risk assessment. So quantifying your emissions to make sure that your air toxics will be used in a predictive modeling assessment to look at what the potential impacts are on your neighbors. And then odor impacts, likewise, are done kind of similar to a health risk assessment. We'll talk about that more later. And then monitoring and record keeping is all dependent upon what your emission levels are. So overall, the higher your emissions are, the more regulatory requirements that you will need to meet. So air toxic considerations. What the air toxic emissions are used for is for a health risk assessment. Each district will, depending on the size of your project, but almost every project will need to do a health risk assessment. And if you have impacts, or it's really potential impacts to your neighbors, then the project may not be permittable. So you need to make sure that the toxic emissions are low enough that you can show that these health risk assessment modeling analyses will not impact the neighbors. Things that you need to consider are your design and emission controls. Even consider the fact that the diesel emissions from things like screeners and grinders, if you can use electric, that's a lot better. Diesel particulate matter is a highly toxic chemical combination. Composting, we've seen projects where the ammonia, the hydrogen sulfide, and the polyaromatic hydrocarbons cause pretty high impacts to the neighbors. So again, for those it's a siting consideration. Consider maybe having a little more distance between you and your neighbors would help on that. And odor impacts and mitigation. Odors are regulated through the districts as a nuisance, but you may need to have an odor abatement plan, and that may be required for either CEQA or permitting. And there may be a need to show modeling that it will not impact the neighbors, depending on the proximity of the neighbors. For odor modeling, you can use the same assessment that you use for toxics if you use a surrogate like hydrogen sulfide or ammonia as one of your surrogates. Odors. Well, as you know, odors come from a variety of chemicals and combination of chemicals. Most of the time, the odors are considered as nuisance as opposed to a health hazard, but they can be both. So an assessment of potential odor can be done using surrogates, such as I said, ammonia or hydrogen sulfide. And so this one thing you want to consider. You'd want to consider odor controls for air permitting. So a lot of times they're the same as your VAC controls, maybe carbon absorption, thermal oxidizers, wet scrubbers, biofilters, et cetera. You can also use odor minimization strategies such as more location or distance to neighbors, design features like enclosures or covers, or even misting can be effective. Odor modeling. If you need to go down the route of odor modeling, you would use a Gaussian plume model like the figure in the bottom corner. It parameterizes the plume spread as it goes downwind from the source, be it a point, area, or volume sources. Areas and volume sources can be used for your compost or piles, and points are generally stacks. Odor modeling for CEQA, so as the plume, I guess I should say, as the plume extends downwind, the plume expands both vertically and horizontally, and then it dilutes as it goes downwind. And so the odor modeling is either used surrogates or it uses a dilution to threshold concept, which is basically that how many times that an air sample must be diluted until the clean air is no longer, until it's no longer detectable. So many agencies in California use a dilution to threshold factor of 5, which means 5 parts of fresh air to 1 part of odorous air until you're down to a level that's not considered terribly odorous, I guess. Odor controls, oops, I think I'm going backwards. Okay, odor modeling. Here's an example of odor modeling, some results. You get the concentration and you look at, compare it to certain thresholds. One of the things to consider is that odor detection thresholds are quite subjective, and every agency likes to come up with their own. So this, for hydrogen sulfide, for example, the 0.008 ppm is South Coast nuisance threshold, whereas this is an odor threshold, whereas a health threshold in California, we have an ambient air quality standard for hydrogen sulfide, which is 0.03 ppm, and so much higher than that odor threshold. So you can see that this is not at all health impacting at this level. You can also do odor monitoring if your facility is existing to confirm that there isn't an odor issue, or that there won't be impacting if you have an expansion, for example. Odor monitoring can be done with SUMA canisters, where you could take that and get your VOC or air toxics also with that. You can use the nasal range finder, which is really fun. That's that nose cone thing to get your dilution to thresholds factors, or real-time monitoring. You've got a permanent or a handheld. At Yorke, we did an H2S odor monitoring network. We set up six stations with hydrogen sulfide monitors around. This was around a wastewater treatment plant, and this was an interesting challenge because it needed to be able to measure extremely low levels of hydrogen sulfide, so that at an odor detection level, but also be able to provide real-time notifications. As you can see, it came in on a smartphone. The reason the monitoring network was necessary was because of an encroachment of a new housing development next to the facility. Emission source testing, you can look at doing things like a flux chamber if you're looking at composting, storage piles, biofilters, or your typical stack testing for stacks and emission control devices. Most likely, one of these will be necessary once you get your permit as a compliance demonstration. Okay, back to emission limits. So back to emission factors and understanding, they have such a trickle effect through your permitting that is really key to develop early in your permitting what your emission factors that you will be using are. A good way, you can obviously use default emission factors that the district approves or you've got from literature, but maybe source testing from other facilities might be helpful. The one thing you have to be careful on that is that emission factors are, and source testing needs to be representative of your process and your feedstock, so those can be really variable. Once you do have your permit, then a compliance demonstration will be required through testing. Process monitoring. So this is once you have your permit, you'll be needing to do some process monitoring. Things to consider is that when you're negotiating your permit conditions, that the monitoring that they're requesting can be onerous or costly, and so you'll want to make sure you negotiate in your permit reasonable monitoring considerations. Here's an example of a composting facility in the Bay Area Air Quality Management District. Here, the district decided that they didn't have much experience with composting, so they basically threw the book at them and said, here's your onerous list of monitoring requirements, including frequent testing for VOCs, toxics, and ammonia. Composting projects. So composting typically is performed in one of these types of methods. In California, windrows are most likely no longer considered back, so you probably couldn't get a windrow permitted in California anymore. This is due to, and because of this, now composting is no longer considered a fugitive emission. Thus, the emissions from a composting facility need to be considered in your emission ERC offset inventory. So before, if they were fugitives, they weren't necessarily in that inventory. So some agencies are considering that in-vessel composting is now the lowest emitting option. So if you don't use in-vessel composting, you have to do a cost-effective analysis to show why you're not going to use. And that was up in the Bay Area. So key factors with composting projects. Composting default emission factors can be very large for VOCs, ammonia, and toxics. And so you can, maybe you might want to consider source testing, but then there's the challenges of source testing composting because of the different stages that you may need to look at to get a representative sample. Each air district deals with composting completely differently. So that's always fun too. And in some districts you need ERCs because of the size of your project or not. And so whether the availability for ERCs in the district will be a driver for you. So you'll be looking at VOC ERCs for those facilities. Health risk modeling and odor modeling, we found that due to using some of the default emission factors can actually be problematic and not be able to actually permit as designed just a regular composting facility. So the need to develop better emission factors is definitely in order right now. Waste to energy projects. So most emission sources at a waste to energy project are controlled. But emission factors are not necessarily well developed for these facilities because they can vary by conversion technology, energy generation, and feedstock. So each one of those needs to be considered when you're looking at waste to energy. Here's an example of an extremely small project in Central Valley. They were using agricultural feedstock for gasification. They're only doing 3 100 kilowatt engines, so 300 kilowatts of electricity generation is quite small. In this particular example, because the air district didn't have a good understanding of the gasification technologies, they decided that the air toxic emissions should be assessed as if for the combustion sources, for the engine and the thermal oxidizer, as if it was a biomass boiler, plus adding some natural gas combustion in there, plus adding the metals from a fluidized sewage incinerator. So they kind of threw the book at it and said, well, here's all the toxics that are going to come off of this. And because of that, the health risk assessment just barely passed. But these are 3 very small, you can see trailerable units. And so needless to say, they had to do source testing for toxics so that they could prove that the toxic emissions are not of that level because they want to be able to permit more of these units and maybe bring some more units on that same site. So on this one, the project was so small, ERCs were not needed. So that was a good, at least one benefit. So keys to success. Keys to success in permitting in California, well, and probably anywhere, is to make sure that your project is well designed. Get it done, well begun, half done. So get it all designed and finalized before you start in on the permitting process. Your emission quantification is going to be a fairly significant aspect to it. You're going to want to make sure that if you can get site-specific or specific to your feedstock or your technology, some emission factors developed before you get started on the process. Make sure you've got your control technologies selected early also. And then understand once you do get the permit what the cost of compliance will be in the state of California. Big issues, big issues can be the offsets. It's quite costly to get ERCs, especially if you're looking at composting projects because the VOC emissions are can be quite significant. Toxic air contaminant emissions can be significant, will drive your health risk assessment. So anywhere that you can work on getting more accurate reflection of what your process is, it's much more helpful. Odors are a high-profile issue, but they're also for control technologies from the district, from a potential nuisance side, and also from a public perception. So you'll want to get that under control early on in the process. And then very large projects, because of the lack of familiarity with these in most districts, you may need to consider a little more extended timeline for permitting these, just so that the district can wrap their head around these. So invest early with the air district and keep them updated. All that said, you can permit these. We do permit the organic projects in California, and they are doable. Thank you.
Very much, Julie. Do we have any questions? Yes.
Yes.
Can you go back to slide 61, please? If that's possible.
Okay.
Okay. Looking at the best available control technology, tell me if I'm wrong. Is that telling us what we have to do and how we have to do it? Because
No.
that's, okay, if it's telling us how, then I have a problem with that, because I don't know if a government can tell us how to do something, just what we have to do.
So, for example, let's take an engine, or maybe a turbine's easy. So if you've got a couple megawatt turbine in California, you're most likely going to be required to put on SCR, selective catalytic reduction, and or both oxidation catalyst. So maybe a three-way catalyst can do all of it. But what the district will tell you is that that turbine needs to meet, be it depending on your size of your turbine, so probably anywhere from 2 ppm NOx to 9 ppm NOx. And so you need to figure out if you want to do SCR, NSCR, or some other methodology. So it's not telling you exactly which one, but it tells you that you have to be able to get down to whatever the emission levels are. Yeah. And like I was saying with the composting, so if you are looking at a windrow and they say, no, you really got to use in-vessel composting, you can do a cost-effective analysis depending upon the size of your facility, so on your emissions that come off of it, and it's a dollar per ton of what your reductions would be to go to a different technology. And so if that's no longer if it's not cost-effective, then it's not necessary to go use that technology. Yeah.
Do we have any more questions?
I think everybody wants to go to the bar.
I think so too. Let's give one more big hand to all of our speakers. Thank you very much.
Thank you.
Thanks for sticking around, folks. I know it's been a long day. A lot of information, a lot of presentations to gather. We did move the bar up and open, so you're welcome to go next door and enjoy some livelihood. Thank you.